everybody. This is our last volume method this week that we'll be taking a look at. It's called volumes by cross-sections. So unlike volumes by discs and washers where we rotated a rectangle around an axis and created a disc, this time we're not doing any rotation. So there are some shapes that we would like to find the volume of that aren't a result of rotating something around an axis. So if there isn't an axis of rotation in a shape, then more than likely we could do this other method. Excuse me. So this is called cross-sectional or slabs. I've seen it, heard it called a bunch of different things, but take a look at this. So let's say we have a parabola here in the first quadrant. Blue line is the x-axis, and back out here. Blue line is the x-axis, and this dotted, this is the y-axis. It actually doesn't matter what the vertical axis is. But we're looking at the coordinate plane with the blue line here. So normally we would take these rectangles and rotate them around the x-axis. But in this instance, we're going to lay this on a flat table. And we're going to take this region, sitting it on our table, and we're going to put three-dimensional shapes on top of that region. So if I go and lay this flat on the table, what I'm doing is I'm going to be drawing or creating semicircles that span from the x-axis up to the function. So the semicircle will come up as tall as whatever half of this distance is. That's the diameter. So then the radius would be this distance here to here. And it's got a little thickness. This is actually a three-dimensional figure. So the width of this little slab or this semicircular piece, cross-section, has thickness. And that thickness we usually call dx. And so I would want to calculate the volume of this shape. Well, this is just a right object, right object, where all I have to do is find the area of this semicircle and multiply it by its width. Well, then I'm going to want to sum them all up, an infinite number of them, because I want this width to become very small. And so the integral is going to come into play. So we're not doing a rotation. We're really like stacking shapes on top of a base region. In this case, the base region is being bounded by this quadratic function right here. And I can do that with a bunch of different shapes. Let me back up here. I lost my, let me go back to this again. It's up. There we go. So now here I have cross sections that are squares. So those are different squares. And so I can then do other shapes like here's a triangle or an equilateral triangle. So again, these shapes are stacked up and you can see it creates these pretty interesting three-dimensional shapes when you stack these up. These shapes are perpendicular with the x-axis. So there is a semicircle. We'll do semicircles, equilateral triangles, squares, and then rectangles. Well, rectangles are just multiple squares stacked on top of each other. Now you could go to more and more side lengths and then sum them all up. But for AP Calculus A, B, and BC, you only have to know those shapes. And again, we would be summing them up all the way through the use of an integral. So kind of a cool concept. So let's take a look at how this works with a formula and develop our formula here. Switch to my paper here. All right. So again, what we're basically doing is taking a region bounded by some function. So I'm going to take this region, let's say right here, within the first quadrant, and I want to stack any kinds of shapes on top of this triangular region. Well, they all start out the same way, and luckily they start out the same way as our discs and washers were, with a nice little rectangle. That rectangle in this case is going to have a dx. This point right here, again, recapping from what we did with discs and washers, it has a coordinate that corresponds to the points on this function. It has an x and a y value. And what I'm going to wind up saying is that this rectangular region is going to serve as the base for all of my shapes that I'm going to stack on top of it. Now, in this particular case, I have it perpendicular with the x-axis, and we'll do ones where we're perpendicular with the y-axis. But I could stack any kinds of shapes on top of there. So I could just kind of draw here. I could draw squares. Let me try to do this pretty well. So little prisms on top of there. And I'm going to eventually do rectangles and things like that, and we'll do that here in a second. But basically, whatever shape that I put on top of this, no matter what it is, I need the volume of that shape. And the volume of any of these right objects is basically the area of the base times the height. Well, the area of this cross-sectional base depends upon what the shape is. If it's going to be a square, triangle, or some other shape. But the height is always going to wind up being dx or dy. That's going to be my little width of my base. And what we want to do is we want to actually develop these. Well, we're going to develop these later. But you can write these all in terms of the base itself. So for instance, if this is the easiest one, if I'm going to be stacking a square on top of there, so the volume of this square shape, well, is the length of this side, which is called y, or what I will call the base. That length, that vertical distance right here, that length is the base. Well, the volume of this is going to be base times height, or the width. So the basic integral here from a to b, those being x values, with the width of dx, is simply going to be base squared. So base squared, that's the area of a triangle, side times side, times its width, dx, would then give me the volume of one of these slabs, and obviously integrating them sums up an infinite number of really skinny little slabs there. Put a little dx down there. Well, a rectangle, all we're going to do is wind up then stacking multiple squares on top of each other. So whatever this is, if I stack a square on top of it, I'm going to then stack another one, and another one, and another one. So it forms a nice big long rectangle stacked up. Now again, this is coming up off of my paper, like I had in my model. Well, that just depends on how many of those squares that you're going to multiply by. And that'll be some constant. So whatever this base is, well, one of these slabs is basically a square, but I might have multiple squares. So I have some constant times basically my integral. And I'm going to say dx or dy. An equilateral triangle is an interesting one, and what we will do at another time, or if you would like to explore, basically what I'm trying to do is to find the area of this side. Remember, this is going to be my width dx or dy. This length is base. In fact, these all are base. And I need to know what the height of this is in terms of the base. Well, oh, maybe we'll just take 2 seconds and do it. So if I call this b, or actually this is going to be half of b right here. This length is going to be b, and this is h. I can do a quick little Pythagorean theorem. H squared plus half of b squared, plus equals the hypotenuse, or the base squared. So h squared equals b squared minus 1/4 b squared. So h squared is 3/4 b squared. So therefore h is the square root of 3 over 2, square root of that, b. So therefore the height is square root of 3 over 2 times the base. So the area of this rectangular triangle, or this triangle, is 1/2 the base times square root of 3 over 2 base, which is my height. And so I get square root of 3 over 4 base squared. And so that's my equilateral triangle. So square root of 3 over 4 base squared from A to B. dx or dy. Notice what I'm trying to do. I'm trying to write them all in terms of the base squared. And semicircles, in the end, again, if you would like to explore, it winds up becoming pi over 8 base squared dx or dy. So in terms of the area of a square compared to a square, if I were to turn this square into a semicircle, it would be pi over 8 as much volume as what was inside of this square. Again, encourage you to maybe play around with that calculation. All right, so let's take a look. So base is bounded by y equals 2x. So here's y equals 2x. X equals 1. And y equals 0. So here's my region in the first quadrant that I'm going to be stacking my shapes on. And what shapes am I doing? I'm doing cross-sectional squares perpendicular to the x-axis. All right, then that base along here, well, that base, this is x and this is y. My formula for a cross-sectional square is base squared. Have a width of dx, so I'll put in a dx. Well, I know I'm going to be stacking these from 0 to 1. That's my x values. And what is the length of the base? Well, the base is notated as y. And I can't anti-differentiate that because I've got an x as my variable of integration, but I've got a function that's in terms of a y. Well, what does y equal? Y equals 2x. And this calculation gives me the actual volume of the area, or volume of all of those squares stacked up on this triangular region. Really teeny tiny little square slabs coming up off of here. But once I get to here, I'm going to have really tall squares coming up off of there. And this is obviously a pretty easy integral to do by hand. So we get 4x cubed over 3 from 0 to 1. So 4/3 cubed units. 4/3 cubed units is the volume of that shape if I were to create it. It's kind of fun and interesting. Let's try another one here. Base is bounded by a quadratic and a linear. That's interesting. All right, let's take a look. So there's my region now. So it's bounded by those two functions. So this is y equals 2x, and this is y equals x squared. And this is the region that I'm going to be stacking shapes onto. And what am I stacking? I'm stacking equilateral triangles perpendicular to the x-axis. So I'll put in my little rectangle. And up off of that rectangle are going to be equilateral triangles coming up off of my paper. Really short ones here because there isn't much of a width. The tallest ones are going to be in the middle, and then they're going to start to get skinny again. So this shape's going to kind of come up off of my paper and go back down, if you can imagine that. Well, equilateral triangle, the one we just did, is √3/4 base squared. Width is going horizontally, so that's a dx. So what is the length of the base? The base is this length of the rectangle. Well, the distance from here to here is merely a difference between the two functions at each individual x value. So square root of 3/4, oh, where am I going? I'm going from 0 to this point of intersection. Oh, where is that? Let me set them equal to each other. X squared minus 2x, and I can already see it's going to be 0 and 2. So from 0 to 2. And again, the length of the base is the difference between them. So which one's on top? The linear's on top and the quadratic's on the bottom. Squared, there's my base squared. Now if we happen to actually get these backwards, won't really matter because I'm going to be squaring it anyway, so it's going to come out to be positive. And if I do that, what I'm going to do is if I punch this into my calculator, the integral, and then just multiply by √3/4, I think I did this earlier, and you can do it too. You can pause now and just try punching it in. This came out to be 16/15. So in the end, it's 4√3/15. And this is a volume. This is cubic units. We obviously aren't working with any units here, but that is a volume. It's kind of cool. Pretty easy, actually, too. So the hardest part in these is literally figuring out what the length of the base is. That's really the tough part in these. So I got a base bounded by -x plus 2. So there's that coming through there. And x equals 0, there's my y-axis, and y equals 0, there's my x-axis. So I'm talking about this region in here. Well, what am I putting inside of here? I'm putting in cross-sectional rectangles perpendicular to the y-axis. Ooh, fun, we're going this way. So that's going to be a dy. And the rectangle is going to come up off of my paper 3 times as tall as much as it is wide. So there's as if it was a square, but there's another square stacked on top and another square stacked on top. And again, these are literally coming up off of my paper. Just trying to draw in a perspective coming up. I guess I should be drawing them and getting bigger if the perspective is coming towards me. That's why you should take an art class. All right, so my cross-sectional rectangles formula is some constant. I'm going to go from a to b, base squared, dy or dx. In this case, I know it's a dy. I already labeled that. And in this case, this length of this base, this point right here, we would label this as x and then y. So I already know that this is going to be x squared. My limits are y values, so they're going from 0 up to the y-intercept, which is 2. And the constant, well, remember, this is calculating right here, just a square cross-section. Well, how many squares do I have stacked up? Well, I have 3 of them. But now the problem is that I've got a function integral in terms of y, but the function's in terms of x. Well, what does x equal? When I go up to here, x is apparently equal to 2 minus y. So I go in and replace 2 minus y squared dy. Limits are in terms of y, functions in terms of y, differentials in terms of y. We are all set to go. And punch that into your calculator. It's exactly 8. At least that's what I got. 8 cubic units. Again, that's not just this one stacked up, it's all of them inside of here. That would be stacked up like my 3-dimensional shapes I was showing you in Desmos. All right, last one. I like this one. I like them all because I made them all. All right, so the last one is, we've got a function y equals 5, so that's just a nice, pretty constant. And the x-axis, so the region bounded between these two on the interval from 0 to 4. All right, so I'm talking about this region here. And what am I putting here? I'm putting cross-sectional semicircles perpendicular to the x-axis. So perpendicular to the x-axis, and I'd be putting semicircles on top of here. All right, so I started with my semicircle formula. Pi over 8, integral a to b, base squared. In this case, it's going to be a dx. I think it's pretty easy to see that this is going from 0 to 4. So what's the base? Again, the base is this length. Well, look at that. Our base, well, I could call it, if I'm going to do exactly what I did before, that's x, this is y. So I could call this y squared. But what is y? Y is 5 squared. It's a constant. Sounds kind of interesting. So we can do this one by hand. So antiderivative of 25 is going to be 25x from 0 to 4. So I'm getting 100 pi over 8, or 25 pi over 2. That's my volume. But wait a second. If you think about it, if I stack semicircles with a constant width or diameter all the way across, what am I really getting? Yeah, I'm getting half of a cylinder. So a half of a cylinder So volume is going to be 1/2 pi r squared h. So 1/2 pi. All right, what is the radius? Well, the radius is just this distance from here to here. Well, that's always going to be 2.5. And the height of the whole cylinder, or half a cylinder, is going to be 4. And if you grab your calculator, take 2 squared times 2, you get 25 pi over 2. You get the exact same thing. So some of these, we really actually don't need a method like this, but it's nice to do a little check. So I've got a couple for you to play around with, some interesting ones, especially towards the end. So play around with those and then check those with mine online and let me know if you got any questions.